Hey guys, this is the foldables, right? So this is our chapter 9 foldables. We always do foldables the class before the test. So let's take a look. We see here that our kite is probably the first one that's very, very obvious, right? Our square. Parallelogram. Isosceles Trapezoid. This would not be an isosceles trapezoid unless it had these arrows here, right? So these arrows are this, a trapezoid by definition is exactly one pair of parallel sides, right? And then a parallelogram is by definition two pairs of parallel sides. So that's why we're seeing here two pairs of parallel sides. And all these, even though it's not marked, all these do also have two pairs of parallel sides because they are under the family tree of parallelograms. So all of these are quadrilaterals, right? And so here's our rectangle, our rhombus, and we've now characterized every shape. But we've had this in previous chapters, right? So what's new in this chapter is that we want to be able to prove, maybe using graph paper or something, that it's a rectangle. And we want to do it mathematically, not just purely going by looks like. So in order to do that, we'd have to know the definitions. So if we think about it, the definition of a parallelogram is this definition right here. Two or both opposite sides parallel. The definition of a rectangle is all equal right angles. Right? And so even though the square has all right angles, it's because it's the descendant of the rectangle, right? It takes on those properties. So a rhombus, we notice, is by definition all four equal sides, right? And our square is the combination of both of those attributes, right? So our square by definition would be all four equal sides and angles, which would require them to all be right angles. All right, so we pretty much took care of the parallelogram family. Now, if we're looking at trapezoids, we're pretty much good to go here. They've already given us our definition. The definition of a trapezoid is right there. It might be good, though, to define it here, right? Again, we're going to say one opposite pair, one set of opposite sides parallel. And to be isosceles, we're just going to add in there the one set of opposite sides parallel and other opposite sides equal length. So I like to think of it as, it looks like an isosceles triangle that somebody just cut the top off of. It's definitely equal sides on the left and the right, and the top and the bottom are parallel. And if it's not oriented like that, we can kind of spin it around and assess it. So the last one, he's off to the side. He doesn't really have anyone in his family, is our kite. But its definition is not solely no pairs of parallel sides, because we can notice that our quadrilateral here also has no sets of parallel sides. So what makes a kite is we define it to be, so by definition, the kite is consecutive or adjacent. Consecutive sides equal length. So what do I mean by that is this side is next to this side, those are the same. And this side is next to this side, those are the same. Notice that's kind of the opposite of our parallelogram. We've got a short side, those are not next to each other, they're opposite, and a longer side, those are opposite each other. All right, so that's all our classifications. Now we're going to think about how this works with our next foldable. How can we classify? So our distance formula, or what I use as my, oftentimes I don't really use the distance formula. I use the formula that my distance is equal to a squared plus b squared. It's the same thing. If you're graphing it, I can actually see what a is. I don't have to subtract the two x values. I actually see the length of this invisible right triangle of Pythagoras's. Okay. But if I can't see the length or I'm worried, I can use my distance formula, right? So let's see how these would help us classify these shapes. Again, why would I need to know the distance? Well, I need to know the distance if, I'm just going to my distance formula, I would need to know if I'm going to classify a kite, because I have to verify that those lengths are equal, right? That this length equals this length and this length equals that. So I need the distance between this point and this point to match the distance between this point and this point. So where else could I use distance? Let's see here. Yeah, I could verify this distance is equal to this distance. So, and I would need the distance formula to verify an isosceles trapezoid. I would need the distance to verify a square, right? All equal sides. So I have to verify this distance is equal to this one, is equal to this one, is equal to this one. And notice I need it for my rhombus. To verify all four equal sides, I would need to know the distance between all these 4 points. So that's how I'm going to use, and when I'm going to use distance, is if I think I've drawn a rhombus, I'm going to need that distance formula or the invisible right triangle. And I'm really going to do that for all 4 of these shapes. Okay, so what's next? Well, my midpoint formula, I don't know when I'm going to use that. So, that's going to be, well, I think there might be a couple times. Yeah, something to do with our diagonals here. So slope, that's the next thing I'm going to need. So my slope formula, when am I going to need that? Well, that's how I verify, that's how I verify if something's parallel, because parallel means same slope. So I'm going to use slope formulas to verify that this slope, like if I look at it here, it looks like it's maybe going up 2 units and over 1 unit. And if I was graphing this on graph paper, notice this looks like it's going up that same incline, right? So slope here would help me verify whether this is the same slope as that, and this flat is also flat, so that would be the same slope. So anytime I'm verifying parallel, I need to use my slope formulas. So anytime I'm verifying parallel, okay, well, I have to verify this line is parallel to that line. So I need it. I need my slope formulas to verify whether or not something is parallel. So it looks like I've finalized a number of shapes here, right? I can figure out a kite, figure out my trapezoids. I can figure out a rhombus and here, but I'm still left with my square and rectangle. So it looks like, you know, my foldables don't go perfect together. But if I look over here, then I think, and we're going to do this foldable in just a second, I think that my slope should also help me verify whether or not something is perpendicular. So if I think about this, if the slope is, let's say, 2/3, then my perpendicular slope, let's say, is 3/2, then this tells me, using my slope formula, that these are perpendicular because they're opposite reciprocals. Now, we also learned in this chapter a second way. It's if their product, if I multiply them together and I get -1. And so notice I do get -1 there. So there's a couple ways we learned in this section, just some other ways to find out if something is parallel or perpendicular. Okay, so as we just said, I can still use my slope formula, so I'm going to use that same color, still use my slope formula to find out if something is a right angle, because it'll have opposite reciprocal slopes. I can find out if it's a right angle because it'll have opposite reciprocal slopes. And now I've classified every shape on my family tree. Nice. Okay, so let's get into specifics of how we'd use these tools with graph paper. And the midpoint is going to be important. We'll talk about that here in just a second. Okay, so my invisible right triangle, or my distance formula, is going to be useful, as we said, when we're trying to figure out if sides are congruent. So they tell us whether sides, right, are congruent, right? They also tell us whether or not diagonals are congruent. So if I look back on my shape here, I know that rectangles have equal diagonals. Squares have equal diagonals because they're a descendant of the rectangle. Isosceles triangles have equal diagonals. The other ones don't. We can kind of see this rhombus. This line is quite a bit longer than this line. Same thing, if this was a stick on a kite, this one's a really long stick, and that's a very short stick. So that's one way we could verify these shapes as well, as that second, using diagonals instead of sides. Okay, what would I use my midpoint for? Well, it would tell us the coordinates of the midpoint of a side. Okay, so that might be useful. It would also tell us whether diagonals bisect each other, and that's probably an even bigger one. So that would be another way to classify shapes, even though, again, we most of the time would use the outer sides and the angle. So let's think about that. Tell us which diagonals bisect each other. So let's take a look. Diagonals bisect. So if I look here, this diagonal does not cut the vertical one in half, but it does cut this horizontal one in half, right? Because if I folded it in half, that side would fold on top of the other. So this distance would match that distance. What other diagonals would bisect? Let's see. Well, a rectangle, yeah, this would cut. When I say bisect, I mean cut these pieces in half. So I'm saying this distance is the same as this distance, and this distance is the same as this distance. All four of those pieces would be equal. Same with our square, and actually same with our parallelogram and our rhombus. So even though this is a very long diagonal and this is a shorter diagonal, this point in the middle is bisected, meaning this length, the shorter diagonal, is cut into 2 equal pieces, that piece and that piece. And the longer diagonal is cut into 2 equal pieces as well. Same is true because it's a descendant of our rhombus. If our rhombus had diagonals, this length here is equal to that length, and this length is equal to that length. They're not equal to one another, but there's 2 small ones that got cut in half and 2 longer ones that got cut in half. So we notice that our midpoint formula would be useful there to classify shapes. Okay, last slope, very important for classifying anything parallelogram or basically anything but a kite. We're going to need our slope formulas. So it tells us if the opposite sides are parallel, right? Opposite sides are parallel. And we need that for our trapezoid and our parallelogram. They will also tell us if our sides are perpendicular. And that makes sense. We need that to classify a rectangle and a square. Lastly, it will tell us if our, this one's a little curveball, if our diagonals are perpendicular. So let's take a look at that one more time before we go to circles, right? So why would our diagonals be perpendicular? Well, that happens every once in a while. We notice with our kite, the sticks of our kite, those are perpendicular. If we look here at our trapezoid, that does not look like a right angle. Same thing here. So that's a characterization of our kite. And it doesn't look like it's this looks like an obtuse angle, and this is an acute angle. So we notice it does happen in our rhombus, and it happens in our square. And the reason for that, this is all a very interesting thing, right? The reason for that is it's because even the rhombus has these consecutive sides. So it's these consecutive sides that are making that happen. Notice our rhombus has consecutive sides equal, and our square as well has consecutive sides equal. So it's the consecutive sides equal that is making this diagonals meet at a 90. So if you notice in your shape, your diagonals meet at a 90, it could be a kite, a rhombus, or a square. So you still need the distance formula to find out the lengths of the sides in order to make classifications. And if you think it's a square, you also then need your slopes to verify these are perpendicular or meet at a 90. Okay, nice work, guys. We got one more. Now our circles. So our foldable helps us kind of separate the 4 different ways that they could ask a circle question. So let's look at the first one. The first one is, how can I write an equation of a circle if they give me the center and, I want to do this one first. Write an equation of a circle given the center and the radius. Okay, so that's the one that's the most straightforward. So let's take a look at that one. If they give us the center, okay, thank you, and the radius, very nice, right? Then that's going to be very useful to us. That's probably the most preferred way we want it. So our general formula looks like this. And they've given us the ingredients. So the center of any circle and my radius can be plugged in. What I mean by that is I can take this number 2 and plug it in there where I see the H. I can take this number 3 and plug it in where I see the K. And I can take that number 4 and plug it in where I see the letter R stands for radius. So that's what we're going to do here, for example, 1 and 2. I'd recommend kind of pausing the video, doing it yourself if you miss class or if you're just trying to study, and then play the video back. Okay, welcome back. Let's go through example 1 and 2 here. So it says that number is 2, okay? And so again, we remind ourselves that it is the opposite of what we might think. A positive 2 looks like we've written it down as a negative 2, right? And a minus a negative 3, using my formula, turns out to be the opposite of what we might think, right? So I see a negative 3 here, and I need to make sure and write a plus 3. All right, and now my radius is 4 squared, right? And so I'm going to write 16, and I call it a day. There's my answer. Voila. All right, let's try another one. So we've got a 0 here, so x minus 0 and y minus a negative 5 using my formula with my radius 6 squared. So here, I didn't go left or right, so I'm still there at just regular old x squared. And here, it listed as negative 5, so I'm going to list that as positive 5. All right, and 6 times 6 is 36. Nice job, guys, right? Okay, so what's another way they could ask us a question as it relates to equations of a circle? So another one is, can you write an equation of a circle given a graph? So what if they graphed it for us? And I think we can do that. That was kind of like example 2 in our lesson yesterday. So let's review. It looks like from my picture, and example 1 and 2 as well, we know how to write an equation if we're given the center and we're given the radius. And we can actually look that up on our graph here. So we can write an equation given the center and the radius. So pause the video, see if you can take it all the way to the equation, and then replay the video to see if you got it right. All right, welcome back. Hopefully you put it on pause. What do we have here? So our centers, let's locate those centers. It looks like I have a negative 2, 1, 2, 3, 4, positive 4. So negative 2, positive 4, and tracking this one, negative 2, negative 1. All right, now let's see if we can find our radius. So it looks like they went over 2, left 2, up 2, down 2, definitely radius 2. And this one we went right 3, up 3, down 3, definitely radius 3. So can we write the equations of these? Absolutely. Just kind of using our example 1 and 2. So let's do it. We've got x, it says negative 2, so we're going to write plus 2. It says positive 4, so we're going to write minus 4. And radius squared. So that would be voila, final answer. Doing the other one here. We have x plus 2 and y plus 1 equals 3 squared. This was similar to our very first example. When the radius is 3, then the right side of the equation is 9 because 3 times 3 is 9 and our formula is radius squared. Well done. All right, just one other half. So what's the other half of our worksheet going to focus on? It's going to focus on the trickier ones. Can we graph a circle? And can we write an equation of a circle given the center and a point? Like any old point. And that makes it a little bit harder. So let's take a look. Okay, so you notice here in 5 and 6, they gave us a center and a point, right? Here they gave us a center and a point. Here, they gave us a nice, beautiful equation, and we have to graph. So I think we know how to do that, especially if they give it to us. It looks like they were nice to us, and they gave it to us in the format we like. So that's our straight form. This is in our general form, okay? So this one's probably a little bit harder. Feel free to kind of pause the video and then see if you got these questions right, 5 through 8. Okay, welcome back. Let's see. The center tells us the left side of the equation. So we don't have a problem there coming up with that part, right? Our center is at positive 2, so I'm going to write minus 2, and positive 3. But then we still don't know our radius, right? And that's where this comes in. By the definition of a circle, whatever the center is, it doesn't matter where it is, any point. This point could be anywhere along that circle. But if they've told us this point is on the circle, then the distance between the center and any point on that circle has to be our radius, right? And that's what we're looking for. So we merely need to know the distance between these 2 points. And we can use the distance formula, or we can graph it and use the invisible right triangle. Okay, so I'm actually going to use the distance formula. I haven't used it in a while, and it is actually good. Good to use now and then. What am I doing? All right, so I'm going to subtract. Let me clear this out a little bit. I need some room. All right, I'm going to subtract the two x values. So 2 minus a negative 3. And then I'm going to subtract the two y values. 3 minus 1. And I get the square root of 29. So our radius is the square root of 29. So if the radius is the square root of 29, then the radius squared would be the square root of 29 squared, which would just be 29. So we can complete our task. Voila. Now, would I do it that way? Probably not. I'm going to be honest. I'm more of a graphing kind of a gal, so I probably would have graphed this. Center is at 2, 3. Point is at negative 3, positive 1. Notice if that is in fact my circle, then my circle's somewhere here, right? Something like that. And this is my radius. So I can find an invisible right triangle right there. And I notice these same numbers are coming up. So if I notice the distance between the two x values, 2 and negative 3, the distance between 2 and negative 3 is the number 5, right? And that's where this number comes from. That's exactly that. It's exactly the same thing. And what is the distance on a number line? Between 3 and 1, well, that's the number 2. So the distance between 3 and 1 is the number 2. So that's where that comes from. So that's why this hypotenuse is the same thing as 5 squared plus 2 squared. And that's how we got the radius to be the square root of 29. All right, next one. Example 6, kind of the same thing going on here, right? We know the center, so we know the front part of our circle equation. But we don't know the radius. So again, you can use the distance formula or you can kind of use graph paper. Negative 2, negative 1. That's going to be my center, and my point is at 0, 6. So 1, 2, 3, 4, 5, 6. All right, and we can draw an invisible right triangle between these two, and that's going to be our radius, right? And we're solving for that. So notice I went up 6. Well, that's the distance between negative 1 and 6. Negative 1 and another 6, the distance between those is 7. Now, what is the distance between negative 2 and 0 on a number 1? Well, 0, negative 1, negative 2. That's this number 2. So the length of this radius has to be the square root of 2 squared plus 7 squared because it's the hypotenuse. So our radius is equal to that. Interesting. So if our radius is equal to the square root of 59, then our radius squared is equal to the square root of 53, excuse me. Then that's that, right? Which is just plain old number 53. So we're ready to finish out our equation. If r squared is 53, we can plug in 53 here. Voila. Okay, so last one, they'd like us to graph these. So again, I hope you paused it and tried this out on your own. I feel like we're pretty good at this. All right, so I see -3, so I'm going to put +3. I see -1, so I'm going to put +1. I see a 9, so that means the radius squared is 9, which tells us that our radius has to be 3. Okay, so 1, 2, 3, 1. There's our center. And our radius is 3. So I'm going to go 3 to the right, 3 to the left, 3 up, 3 down. Bada boom, bada bing. That's a circle. Sweet. Now let's graph this other one. So I've got a -1 and a positive, a -2. So a big +2, a +1, so -1. And our radius squared is 25. So this came up a couple times, right? So if I take the square root of both sides, I find out that the radius is 5. So I've got my ingredients to graph. Center is 2, so 1, 2, and a -1. So there's my center. And my radius is 5. So I'm going to go 5 to the right, 5, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There you go, right? Ooh, there it is. Nice work, guys. Good luck studying.